like to start with a quote by Gertrude Cox. She was a famous American statistician born in the 1900s. And Gertrude is saying that statisticians might think that they're mainly going to contribute to the statistical theory when helping you to plan a study, but in fact their most valuable contribution is encouraging the investigator to explain why they want to do the study. I mean, we have mentioned this before. If the research question and objectives are clear, the design, sample size, and analysis plan will flow from them. And a statistician can help you all the way through your grant applications, not just doing the power calculations and the statistical analysis plans. So we'll now consider how we can help you with the study design. So study design is very important. If you choose the wrong design for your study, you may not be able to use the results. There are two main types of design: observational, which is non-experimental studies, they don't involve an experiment, and intervention or experimental studies. For both of these, you can collect information on groups of patients, such as GP practices or schools or any group of patients, or you could collect data on individual participants. There are advantages and disadvantages of each type of a study design. For example, if you want to compare a drug to a placebo, you'd use an experimental study, in other words, a clinical trial. But if you wanted to run a study that monitors the growth of children from birth to 10 years and the factors that might influence that, you'd use an observational study, in this case, a cohort study. So in observational studies, you're not intervening, you're just observing. So the funding panel will expect an explanation for why you chose this study design. So you need to think together with a statistician about questions like, has a clear rationale been provided for the study design? Have patients, service users, carers and relevant stakeholders been involved in the design? And why this design is the most suitable for your study. Before we can work out a sample size, we first need to understand what question you are trying to answer. Ideally, this question will clearly state the primary outcome of interest, and if not, a statistician is going to ask you about it. The type of research question we're asking dictates the broad type of sample size justification we carry out. On this slide, there are examples of two common types of questions: descriptive and comparative. A descriptive question aims to describe a certain parameter of interest rather than compare groups. For example, what's the prevalence of sedation in critical care units? What is the association between self-reported and measured physical activity? What are the recruitment and dropout rates? As we saw, this is extremely useful before running a full trial, and it's often called a feasibility study. On the other hand, a comparative question is going to look at differences between groups by comparing one group to another. For example, the research question could be, is a strengthening and stretching program for people with rheumatoid arthritis better than current care? Or is drug A better than drug B for a certain disease or illness? So we'll now look at what you need for the sample size calculation for each type of research question. So, descriptive studies, we'll start with these. The statistician will need to know about the analysis you want to perform in your study. So this should be clear from your research question, and if not, a statistician can help you to clarify it and phrase it correctly. As in the previous example, if your descriptive research question is about the association between self-reported and measured physical activity, then a statistician would advise you to look at the relationship between these two variables by analysing a correlation coefficient between them. A correlation coefficient would then be the statistic of interest. For the actual sample size calculation, you will need to decide on a planning value. Note that the sample sizes for descriptive studies are precision-based, therefore you also need to decide on the level of precision that you want. We're going to talk about what a planning value actually is and precision level in the next few slides. So we need to find a reliable estimate of the correlation or proportion of interest so that we can find out how many people you'll need to recruit for your study. You'll need to have some prior information about the value you might expect, and this is your planning value. Based on this, you would then build your precision estimates. So where should your planning value come from? Well, you could mostly rely on previous literature, or you could run a pilot study before your main descriptive study. If there's nothing that's available for you to use, you could come up with the worst case scenario to ensure that the precision is no worse than some desired level. We'll talk more about precision on the next slide. So what do we mean by precision? Well, it's essentially a confidence interval with a lower and upper limit, which defines an acceptable level of precision around your planning value. So you could use a precision of 99%, 95%, or 90%, but 95% is usually used. So a confidence interval is a range of values calculated from sample data that it's likely to contain the true value of an unknown population parameter, for example, a mean or proportion, with a specified probability, 95, for example, 95%. And if this is the first time you've met a confidence interval, I don't really expect you to be able to understand it from what I've just said, but obviously your statistician can talk you through that during the study. So we'll look at the example of a precision-based sample size calculation on the next slide, but remember that the choice of the width of the confidence interval should be justified in your grant application. It's usually clinically driven so that you can draw meaningful conclusions from your sample. So a statistician would usually come up with a range of scenarios for the precision-based sample size calculations, depending on the planning value and the desired confidence interval width. The example on this slide is based on a proportion as a statistic of interest. So if, for example, some studies suggest a proportion of 0.3 or 0.5, then you could identify different sample size scenarios depending on whether you want a more precise or a less precise estimate. The narrower the width of the confidence interval, the more precise the estimate is and the bigger the sample size required is. For example, if you narrow down the width from 0.2 to 0.1, you would need to increase your sample size by almost 4 times, as you can see on the slide. To choose the sample size from these scenarios, you need to think about how much does it matter to you to have a wider range of values estimated around the expected value? What width would be clinically meaningful, and how many participants can you realistically expect to recruit for your study? So now let's look at sample size calculation for comparative studies. In order to do a sample size calculation for a comparative study, the statistician needs to know about the type of study design, the effect size, a measure of the variability, the desired power level, and the desired significance level, which is actually also known as the type 1 error rate. We'll talk about that later, and it's usually taken at the 5% level. So we need to know quite a lot, really. We'll talk about each one of them separately on the next slides, but you can already see that a lot of thought goes into how you calculate the sample size for comparative studies. And that's why it may seem like statisticians have a lot of questions to ask you when you start writing a grant application. So let's start with the study design. There are many issues relating to the design of a trial that can affect the sample size calculation. For example, the number of groups you will have in the study, whether you will have repeated measures on the same people, or whether the groups will be independent, in other words, different people in each group. Also, the type of primary outcome from the study is very important because the sample size calculation will be completely different for continuous, categorical, or survival outcomes. If your study is going to be a trial, then the type of randomization would also need to be accounted for. Whether you randomize patients individually, or, for example, randomize GP practices to adjust the expected correlation between patients within the same practice. Next, I'd like to talk about the effect size, which is essentially a numeric value of the difference between the groups which you expect to find in your study, and it's expressed in the units of the primary outcome. In a well-designed study, this is equivalent to the effect of the intervention or behaviour of interest. Why do we need the effect size? Well, should this effect actually exist, we want a good chance of ruling out of there being no effect. So in other words, if we observe this difference in our study, then we want to be able to say that the result is statistically significantly different between the groups. In the case of clinical trials, the choice of effect size for a sample size calculation should be the minimum clinically important difference, which we'll talk about in the next slide. So how would we know which value to use for the effect size of your study? For a sample size calculation, effect sizes are not what you hope or expect to see, but it's a minimum effect size which would change clinical practice. So you'd first look at previous studies related to your field of research, but you'd also talk to clinicians about the smallest value that would lead to a change in practice. So for example, if your primary outcome is mobility for COPD patients, somebody might already have established the minimum clinically important difference for this outcome. For example, there's literature that suggests changes between 15 and 60 metres in the 6-minute walk test for people with COPD is important. In certain areas of research, people have done work on different outcome measures to define the minimum clinically important difference, so you should definitely check this when designing your study. Otherwise, this is a decision for the clinician. In certain situations, a statistician might be able to help with a more generic approach that doesn't require clinical judgment or previous literature, but you need to discuss it with your statistician and make sure that it's in context for the condition you're looking at and what this would actually mean for the patients. However, remember it's your responsibility to choose and justify the effect size for your study. It's not the statistician's responsibility. So this graph shows how the effect size you choose influences the sample size. So the y-axis going up the side represents the sample size, and the x-axis going along the bottom represents the effect size or the difference between the groups. So you can see that larger effect sizes lead to requiring less people. An effect size that's too large may also raise suspicions that you're uncertain about your ability to recruit. It's rarely sensible to adjust the effect size purely to save numbers. The smaller the effect chosen, the larger the sample size will need to be. This is why it's important to select the minimum clinically important difference for your study. A bigger difference will lead to a smaller sample size requirement and may mean you cannot show a smaller difference than this to be statistically significant. You don't want to get to the end of your study and say, well, we saw a difference of 2 units between the groups. This would make a huge difference to patients' lives, but we used a difference of 5 units in the sample size calculation, so we don't have enough people to show the difference of 2 units to be statistically significant. So as a result, our finding looks negative. So the nice little cartoon here about Goldilocks and the 3 bears and about sample size or the effect size being just the right size, not too small or not too large. And if you know the story of Goldilocks, you'll know that Goldilocks was always looking for things that were the right size for her. So the next important factor for the sample size calculation is the variability of the outcome measure. When talking about continuous outcome measures, the variability is most often called the standard deviation or the variance. For binary outcomes, it's called the rate or proportion. If there is a lack of literature, then you could also consider conducting a feasibility or pilot study to find a variability for your main study sample size calculation. You can get an estimate of this from previous literature or studies in a similar area. If you've got a lot of studies to choose from with different estimates of the variance, you should choose the study with the best quality in terms of the sample recruitment and retention. And remember to consider carefully how similar your population is to the population you're using to estimate the value. Lastly, if neither of these options are available, a statistician can help you to apply a generic approach, but you need to make sure that you put this into context and justify why this is the best choice. It's important to note that a larger variability leads to requiring a larger sample size. In other words, more people that you need to recruit. If patients in the population of interest are more different from each other, for example, a wider range of age, This means that your data are likely to be more scattered and you will need to have a bigger sample size to see what's going on in this population. By relying on previous studies, if you've got several high-quality examples close to your population of interest, you could combine the estimates of variability across those studies. Apart from this, you should also think about generalizability. For example, can you then apply your results to this population in practice? Is the estimate of variability you consider appropriate for the data that you're collecting? So, other sorts of questions to consider. So let's now talk about power and error rates. So we usually start with a null hypothesis, and a null hypothesis just means we put forward the suggestion that there's no difference between the groups that we're looking at. So when we use significance tests to make decisions about whether to accept or reject a null hypothesis, we can make two types of errors. We can either reject the null hypothesis when it's in fact true, or we can fail to reject it when it's actually false. These are often labelled type 1 and type 2 errors. So an easy way to picture this is, imagine you're trying to hunt a lion. So you're inside the house and you're going to go out and hunt your lion. So you can hear what's happening outside, but you can't see it. So type 1 error is when there's a kitten outside, but you think there is a lion because that kitten happens to be roaring. So type 1 error is when you think you have a significant result when it's actually not, it's just due to chance. What you equally don't want to have is a type 2 error. So there's actually a lion outside the door, but you can hear it meowing, so you think it's a kitten. Both types of errors need to be controlled in your study to a level which you're willing to accept. Conventionally, power is set at either 80 or 90%, and type 1 error is usually set at 5%. So if the null hypothesis is false, then we can either reject it, which would be the correct decision, and this is often referred to as the study power, or we can accept it, which would be a type 2 error. So for example, you might accept 20% that you get the lion or kitten wrong, and then the power for your sample size calculation would be 80%, 100% minus 20%. Sample size calculations are not a crystal ball, they are just an estimate, which will show to the funder and audience that you tried to be as precise as possible. So here's an example of a range of scenarios of the total sample size required for a study focusing on an effect size of 0.3 or 0.4 for the primary outcome. Notice how a higher effect size required less people. However, the estimated sample size won't guarantee that you'll be able to recruit so many patients. It's only an indication of power and variability. It's your responsibility to know the amount of time required for recruitment and the number of sites needed to recruit the estimated number of patients. The statistician will also talk about it with you to make sure that the estimated sample size is actually realistic for your study. For example, notice how this range of scenarios accounts for the potential dropouts of patients over time after recruitment. And Sophie was talking about this morning. In the next slide, I will talk about other common considerations for a sample size calculation. Besides the dropout rate, other considerations would include the type of follow-up and the type of censoring. If, for example, you focus on survival data like death or progression rates. If you have patients clustered within GP practices, then you need to account for the intra-cluster correlation and the number and size of clusters themselves, which would just be the GP practices in this example. Just a reminder that when we're using observational data for comparative research questions, be aware of confounders if anything is causal in the research association, which you might also need to account for in your sample size. I think one of the classic examples of confounders, it was studies, epidemiological studies from the 1980s and 1990s, where it looked like there was an association between high coffee consumption and certain types of cancer, pancreatic and bladder in this case. So, however, this apparent link was a classic example of a confounding variable because coffee high coffee consumption was actually confounded with tobacco smoking because people often sit down to have a cup of coffee and a cigarette. So that's what I always think about confounding in that sense. Is there something else which is really influencing the association much more? So as soon as you put tobacco smoking into the equation between coffee consumption and cancer, the coffee consumption is no longer important. Right, okay. So a statistician can help you with all of these decisions, and you might need several meetings to be able to provide your statistician with more information on the population of interest, your research question, and the sites you could recruit from. For example, as already mentioned, you need to decide on a realistic recruitment period and the number of sites you can use to recruit for your study. The funding panel will expect to see that the proposed recruitment is likely to meet the targets, and you've already consulted patients, carers, and service users about the best recruitment process for your study. You'll also need to think whether the process you propose for accessing, approaching, consenting, and enrolling potential participants is actually ethical and suitable. For example, your population of interest, the health condition you study, or with the current NHS workload. Now let's look at a case study of how to put the statistical aspects of your proposed study together for an NIHR grant. Our case study for today will be the NIHR Health Technology Assessment Programme call. The full information is presented on the right of the slide, but to save our time reading this, I'll point out the most important aspects of this call, which a statistician would need to know about your study. So the aim of this call is to evaluate the clinical and cost effectiveness of physical exercise for treating depression in adolescents. You've already heard about PICO, we covered it yesterday, which stands for 4 words describing a study population. Describing a study. Population, intervention, comparison, and outcome. In this call, the population of interest is adolescents, the intervention is physical exercise, the comparison is no exercise, and the outcome is the measure of the depressive symptom severity. So this call requires applicants to submit plans for a 3-arm study to evaluate separately high and low intensity physical exercise compared to no exercise. It also needs to be a randomized clinical trial. As I go through the various steps involved in putting the stats component of your application together, I'll refer back to this case study to illustrate the points that I'm making. But the points that I make will generally be transferable to other types of health study, whether a clinical trial or an observational study. So this is an example of the statistical aspects you'd mention in your plain English summary and scientific abstract. The plain English summary needs to be written in simple language about how many participants you aim to recruit, in other words, your calculated sample size. However, the scientific abstract should go into more detail about the chosen clinically important effect size, the variability power and the significance level, as well as any other sample size considerations like the dropout rate. So in this case study, the final sample size was 387 participants, which was based on 1, the effect size with a value of 2, which was the difference in means between each exercise arm and no exercise arm. 2, the variability around the estimate, which was a standard deviation of 4.4. The statistical power of 90%, meaning that the type 2 error was chosen at the 10% level. The type 1 error of 5%, which is a significance level. And the dropout rate over time of 20% of the recruited participants. However, you'd need to go into even more details about the statistical plan in your research section of the grant application. Simply put, just saying the total sample size is not enough. You need to explain why you chose certain parameters in your sample size calculation, like the effect size of 2 in our case study, or the dropout rate of 20%. You need to justify the chosen sampling methods and why they're the best fit to your research question. The sample size calculation should be explained in such a clear way that it could be verified by another statistician on the panel. So please don't delete or condense any information that the statistician provided for your study, as it could jeopardise your chances of getting a grant if the panel cannot understand how you came up with the total sample size. Now let's look at the example of how ideally you'd write the sample size calculation paragraph for the example of our case study. I'll start to highlight certain areas in this paragraph to point out the most important aspects. So, first of all, you need to remind the panel about your primary objective. In this case, comparing two intervention arms to the control arms. Control arm, singular, one control arm. And usually in the same sentence, you need to remind them about your primary outcome or co-primary outcomes if you have more than one. And you should also indicate the endpoint at which you collect the primary outcome after you've recruited the participants. So you've got the PHQ-A, which is a measure of depressive symptoms, and that's being taken at 1 year after randomization. You can then repeat the same information that you used in the scientific abstract, but now add the references to the previous study, which these parameters were based on for your sample size calculation. So that's what we've done here. And of course, don't forget to mention any other considerations you had for your final sample size. For example, here we are accounting for up to 20% dropout. Finally, you need to show that you're aware of realistic expectations for the recruitment of patients into your study in terms of its rates, length of time, and number of sites, which would allow you to meet the total sample size target. In our case study, for example, you expect 9 eligible patients per month over the total of 18 months over 10 sites. And this was also discussed this morning. So there's a lot of information the statistician needs to put into that paragraph in the research plan section. Moreover, you should allow the word count of your grant application to include more details on different sample size scenarios which were considered. For example, because of the variety of recommended effect sizes, which you, of course, need to back up with previous literature and your justification of the most suitable effect size for your study. Remember that the most common problems which panel members come across are the sample size calculation is based on a continuous outcome when the primary outcome is in fact binary, or the wrong study design was chosen, or within group comparisons were used rather than between group comparisons, that the estimated treatment effect is too big and clinically unrealistic, or that the sample size is too big to be feasible within the time frame, or that the research team has not taken into account dropouts or treatment crossover. So let's talk about the analysis plan now. Statisticians can write this section for your grant application too. However, you'll need to think together as a team whether the proposed analysis plan is clear and suitable for your data and research question, because this is what the panel will be looking for. The first thing the panel will be looking for in your analysis plan is that it's consistent with your study objectives and your sample size calculation. So, as a reminder, if you're planning to compare groups, as in our case study, then the sample size should be power-based, and therefore the main analysis should be about comparing the groups using a statistical test. But if your research question was about estimating a certain rate or proportion, then the sample size should be based on estimation. So in other words, precision-based, and then the appropriate analysis would be descriptive. Let's come back to our case study on the next slide. So as you remember, the case study has 3 groups comparing 2 types of physical exercise to no exercise. So when you want to explain your analysis plan in plain English, you need to talk in simple terms about the method of assigning the participants to each group, what those groups are, what kind of intervention would they get, and what is the comparison group. You'll then need to mention how long the follow-up period is and what you will measure as the primary outcome. However, you should go into more details about your analysis plan in the scientific abstract, where you can use more technical language. For example, explaining that it'd be a trial with multiple centres with randomization, double blinding, and there will be a superiority approach by looking at both the possibilities of a worse or better outcome than the usual care. Apart from the number of centres and the expected time of recruitment, you'll definitely need to say the statistical method which would be applied in your primary analysis and which significant level will be applied. As a reminder, your statistician will make sure that the analysis plan is in line with your research question, study design, and primary outcome. So, as you can see, a statistician is involved throughout the whole funding application, through all sections. So please be mindful when cutting out words or sentences from your grant application and always double check with your statistician. Unlike the scientific abstract, your research plan will need to be very comprehensive about your analysis plan, which again will be guided by your statistician. You should write here in more detail about how the randomization will take place, how the primary statistical analysis will be conducted. You may also go into more details about other outcomes of interest, and you may talk about how you will deal with missing data. Also, mention here any possible interim analysis and any specific requirements your study has for certain committees, which will check the quality and the safety of your study while it's running. If you're doing an observational study, don't forget to mention potential confounding variables like the cigarette smoking with coffee and the association between coffee and cancer not being correct. Confounding variables are those variables which lead us to draw an incorrect conclusion about the association between the exposure and the outcome. So you can have a closer look at the example on this slide after the presentation. To summarise this talk, let's look at some common problems in grant application that can be avoided with help from a statistician. We said at the start of the presentation, the sooner you involve the statistician, the better chances your proposal will be successful. So you should see a statistician at the start of your project. Ideally, go to see the statistician before you start doing anything. Explain why the research is important and what it is you plan to do. Help your statistician to understand your area of research. For example, it might be helpful to provide a list of definitions and acronyms to the statistician before you meet with them. A statistician can then have valuable input into the design of your study and provide early input into the sample size estimation to help with the study planning and costs. But to help you with this, we'll ask a lot of questions that you'll otherwise be asked much later on. So please take seriously the time commitment of the statisticians. Leave plenty of time for them to help you, as in, unlike the video example, when his grant was due the next day. For example, don't send your statistician the whole application at the last moment, asking them to fill in the sections about power calculations and analysis plan. Also, changing one part of the calculation can lead to rewriting statistical sections, and it's not just as simple as clicking a few buttons. As noted previously, there's still a large part of sample size calculations that requires clinical input. The panel will be looking to see that the analysis aligns with objectives, design, and outcome measures. So removing parts that can leave holes that the panels will question. This slide should help you to understand how a statistician is going to be involved throughout the whole research process. So we've got study development. There's a long list of things that the statistician will be doing. So the development, the setup, another long list of things that the statistician will be helping you with, the study management and the study closeout. There's always things all the way along. So a statistician should be a part of your study team whom you need to trust with your data and findings. Some of the points in these boxes might not be relevant to an observational study, but potentially all of these things could affect the costing of including a statistician in your study. So make sure that you appropriately costed in the statistician's help, that you're realistic about the expected amount of time the statistician will need to be involved in your study. And in your application, you will also need to outline how the statistician would be involved throughout the study. To conclude with another quote from R.A. Fisher. He was another famous statistician, and he was born in around 1890. So he was around at the same time as Gertrude, who we met at the beginning. And he says, to consult the statistician after an experiment is finished is often merely to ask them to conduct a post-mortem examination. They can perhaps say what the experiment died of. And the last thing you want to do is to get to the end of your study and realise that the design is so bad that you actually can't find out what you want to. In fact, sometimes you actually can't find out anything if you have a really poor design. So again, we say, see the statistician as early as possible before you start doing anything. Remember that certain things might be too late to change later once you've received a grant, so you need to have a statistician's input early on. And if you come to a statistician too late, a statistician might want to change things in your study design due to sample size requirements or the analysis issues. This in turn may affect the way data collected and the number of people you need to recruit, which will in the end affect the cost of your study. To avoid such changes in your study design and costings, you need to liaise with a statistician early on. Secondly, even experienced medical statisticians may have no knowledge of your area of research. There are a lot of terms which are not transparent. Again, as I say, it may help to provide a list of definitions and acronyms to the statistician before the meeting. The more we know about the condition and how it's measured, the better our advice will be. Thirdly, we need to know quite a lot about the data. It's not immediately obvious to a statistician just how every clinical variable might be measured. This might be influenced by the state of health of the patient, the laboratory, the analyzer, the person making the observation, the time of day the sample was taken, and even the weather. Because for some procedures, such as spectroscopy, the weather can have an influence because the actual temperature of the day when the spectrogram was run can actually change the answers that you get. So it's important for a statistician to know the sources of variation, possible sources of variation in your data. And finally, remember that a statistician wants to help you. So it's best to make us part of your team and let us challenge you with questions, because at the end of the day, we want your study to be of high quality and change medical practice as much as you do.